All right, here we're finishing up the second part of section 8.1. We're still dealing with confidence intervals, sort of the basics. So we're applying the general rules and the general terminology for confidence intervals still. All right, so interpreting the confidence levels and intervals. So the confidence level tells us how likely it is that the method that we use to take a sample, calculate the X bar, create a confidence interval around that X bar, how often or how likely that is to capture the population parameter. You have to be careful because even though the confidence level is written as a percent, it's not a probability. It's not the chance that a particular confidence level captures the true parameter, the true population parameter. Either that confidence interval captures it or it doesn't. We really don't know which one is happening because we don't really know what the parameter is. So it's not a probability or tells us the chance, that kind of thing. It's a 90, often we'll use 95% as our confidence level, but that does not mean that it is a probability or that it is a chance, the 95% chance that we captured the true mean. That is not how we interpret it, and that's not what it means. So be careful with that. All right, so it basically gives us an interval of plausible values for that parameter. It's one way to sort of look at it. We interpret the confidence level and the confidence interval in much the same way, regardless of whether we're doing population means, population parameters, or some other parameter. For the most part, we look at means and proportions, but there are certainly other parameters that you could estimate using confidence intervals. All right, so why do we settle for 95%? So going back to Garfield, remember the price we pay for being more confident is a wider interval. And sometimes the interval is so wide as it is with the temperature prediction for tomorrow's weather, it's so wide to the point where it is really useless. All right, so we're going to take our estimate plus or minus our margin of error. And so we're going to talk about like how we calculate those things more in the next sections. We're going to get into more details and how they apply to means and proportions in the next couple of sections. Here we're still relying on just the sort of the empirical rule. 95% is about plus or minus 2 standard deviations of the sampling distribution. So this is still looking at that same mystery mean. Remember when we had 16 data values and the standard deviation for the population was 20. So 20 divided by the square root of 16, or 20 divided by 4, which is 5. And then since it's 95%, the empirical rule tells us that if we want to be 95% of the samples to be within a certain value, we would want that value to be plus or minus 2 standard deviations. And in this case, it's the standard deviations of the statistic or the standard deviation of the sampling distribution. So the general rule will be the statistic, which is another word of saying the point estimator, or that'll be X bar or P hat most of the time. The critical value is based on the confidence level. So in this case, we want to be 95% confident, so that using the empirical rule, we were using 2. And then the standard deviation is just the standard deviation of the sampling distribution of the statistic. All right, so I'm going to revisit this app. And this app is what is investigating the width of the confidence intervals and the types of things that affects the width of the confidence interval. So we'll revisit this app again. All right, so again, we have the statistic plus or minus critical value times the standard deviation of the statistic. And the statistic is just the point estimator. So that would be the X bar or the P hat. All right, the margin of error. So the margin of error is made up of the critical value times the standard deviation of the statistic, the standard deviation of the sampling distribution. So you choose the level like the confidence level. So, 95%, 90%, 96%, whatever you want to choose. And the margin of error sort of follows from that. All right, the critical value is going to really be based on your confidence level. The standard deviation of the statistic is not based on the confidence level. So the critical value depends on the confidence level, and the sampling distribution, and also the sampling distribution of the statistic. All right, so the greater the confidence, the greater the critical value, and as a result, greater the confidence interval. The standard deviation really depends on the population standard deviation and the sample size, n. So you may have come to the to the thinking like, okay, well, we don't know mu. We're trying to estimate mu, the true population parameter in the mystery mean, for example. We kind of skirted over the issue that we are pretending to know sigma, so the standard deviation of the population. We will not know that, and when we get further into confidence intervals specifically for means, we'll get into the realistic situation where we don't know sigma. But for now, we're sort of pretending we know the standard deviation of the population. Even though we don't know the mean, we're pretending to know the standard deviation. So we'll get past that a little bit and change how we do things based on that fact. All right, let's look at an example here. Admissions director from Big City University found that 107.8 to 116.2 is a 95% confidence interval for the mean IQ score for all freshmen at the university. All right, discuss whether each of the following explanations is correct. So we have A, B, C, D, and E. Some of them are correct, some of them are not correct. Read them and decide. So there is A. There is a 95% probability that the interval from 107.8 to 116.2 contains the population mean IQ for all freshmen. All right, so we already said that that is not a probability. So the 95% confidence, that level does not indicate that there's a probability that we captured the mean. We either captured the mean or we didn't, but we'll never know really whether we did or not. So it is not a probability or some chance. All right, B, there is 95% chance that the interval 107.8 to 116.2 contains X bar. Well, this is wrong because there's a 100% chance that it will contain X bar. X bar is always in the dead center. It's the midpoint of our confidence interval. So it's confusing you a little bit there, so you have to know your terminology there. Okay, C, the interval was constructed using a method that produces intervals that capture the true mean in 95% of all possible samples. So this is true. That's exactly what our definition of confidence means. All right, D. If we take many samples, about 95% of them will contain the interval 107.8 to 116.2. So this is false. There's nothing special about our actual sample here, right? The sample that we got that created that confidence interval, there's nothing special about it. No, it's not going to contain that. Different samples will obviously have different X bars and as a result, different confidence intervals. So nothing special about that confidence interval. All right, E, the probability that the interval 107.8 to 116.2 captures mu is either 0 or 1, but we don't know which. And that is true. Yeah, remember the confidence interval, confidence level, 95% in this case, is not a probability. Our interval, 107.8 to 116.2, either captures the true mean or it doesn't. So it's either 0, it didn't, or 1%, it did. But of course, we don't know which one. All right, a couple last things here. There are two important cautions to keep in mind when constructing and interpreting confidence intervals. Our methods of calculating assume that the data come from a simple random sample of size n from the population of interest. So if you don't have a simple random sample, then you really can't be doing anything that we do in this chapter. The margin of error in the confidence interval covers only chance variation due to random sampling and random assignment if we're going to do an experiment. So what this is saying is margin of error sounds like you did something wrong, and it's not. Margin of error is just the error that comes about when you randomly sample. So you have variability in sample. The X bar is not often going to be the actual true mu value. So there's some sort of margin of error. It's the difference between the true value, true parameter value, and our X bar. And so that's going to vary with every sample. And so that's what we mean when we say margin of error. That does not take into consideration any mistake you might have made in your sampling process, any bias that results in questionnaires or whatever else. It simply refers to the variability in every random sample. All right, so here is your homework. The last couple are multiple choice. Okay, so we're back to this app, and we're going to use this app to play around with and investigate the things that affect the width of the confidence interval. So if you look at what I've got on the screen right now, I have a confidence level of about 80%. I have 25 samples displayed on the screen, and you can see the percent hit or the capture rate of the samples that we have on the screen is about 80%. So, which is what we'd expect because I have the confidence level set at 80%. So 80% of our samples and resulting X bars plus or minus the 2 standard deviations. Well, in this case, it'd be a little bit less than that because we're at a confidence level of 80%, but plus or minus the margin of error, we will capture the true parameter 80% of the time. So what happens if I use this slider to increase my confidence level? Let's take it up to about 95%. So you can see what's happening is the confidence intervals got wider, which makes sense because everything else being the same, we would expect that if we're going to capture the true parameter more frequently, we would want an interval that is wider. So let's just take it up a little bit more. I'm at 98% confidence, and indeed 96% of the 25 samples have actually captured the true mean. So if I increase the confidence level, C, I would expect the confidence interval to get wider because we're more likely to capture the true mean that way. If I take it back down to 80%, this one won't let me go any lower than 80, you can see that indeed they got narrower, and as a result, fewer of them captured the true parameter. All right, let's set that at 95, and now let's play around with the sample size. So how will the sample size affect the confidence interval or the length of the confidence interval? Now with the confidence level slider, I can slide it back and forth, and the confidence intervals stay there and just get wider and narrower. However, when I play around with the sample, when I change the sample, they all erase and kind of reset. All right, so because if sample size changes, the actual sample has got to change because now I'm adding more data values to, or less data values to each of the samples. So you have to rerun those. But you can see, like, if we have 10%, or let's say we can go to 5%. So let's do that. So a 5%, look at the sampling distribution. That's the dashed red thing. And let's do 25. You can see actually our capture rate is kind of low. It's 88%. But, you know, again, if we did this many times, we'd expect it to be 95. But in the short run, we can see some variations from that. So, but what I wanted you to concentrate on now is the width of the confidence intervals. So they're pretty wide when the sample size is 5. Now let's take it up to 100, and now the samples are all going to disappear, but let's look at the sampling distribution. So you can see where the sampling distribution is right now. Now if I take it up to 100, the sampling distribution just got much narrower, which makes sense because the square root of n is in the denominator of the standard deviation of the sampling distribution. So let's sample these. Now you can see I have 25. Again, the sample rate's not always going to agree exactly because we only did 25 samples, but you can see how much narrower they are. This does not affect the confidence interval's ability to capture the true mean. Indeed, it actually went up a little bit. It was 88%, now it's at 92%. But even though the intervals got smaller, the X bars, the distribution of all the samples, the sampling distribution, is much narrower. So we expect the X bars to be more clustered around that true mean as we get larger sample size. So it's not surprising that even though the confidence interval got narrower when you increase the sample size, the X bars more closely cluster around that true parameter. So as a result, we don't really have a diminished capture rate. Let's do that again. We'll go back down to 5 and do a sample of 25. So you can see here, they're much wider. It's capture rate of 92%. In reality, we would, if we did many of them, it'd be 95. But now let's look at what happens when I move it back up to 100 and do another 25. The capture rate isn't really changing. I mean, in this case, it's 100%, but it's just, the randomness of samples is to cause that. But it's that the X bars, even though the confidence intervals are smaller, the X bars are more closely clustered around that mean. So it doesn't affect the sample, the capture rate of our samples.